This is the end, beautiful friend. This is the end, my only friend. The end of our elaborate plans. The end of everything that's done. The end, no safety or surprise. The end, I'll never look into your eyes again. Can you picture what will be? So live and free, desperately in need of some stranger's hand. In a desperate land. Lost in a romance, wilderness of pain, and all the children are insane. Our children are insane. Come on, come on, baby.
I don't know what the last word question is. What is it? What is it asking for? While you're telling me what it is, let's consider this question, right? We have 3 novels, 4 math books, and 1 biology book to be arranged on a shelf where the math books must be together. All right, we'll discuss it. I'll show you what to do. But first, let's consider this, right? So we have 3 novels, 4 math books, and 1 biology book to be arranged on a shelf. I think the understanding is that you can tell the novels apart and that you can tell the math books apart, right? They're not the identical same book. Why would you have 2 identical math books or 2 identical novels? Math books must be together. So in how many ways can you do this? My hint to you was to consider a math group, right? That group has to be together. So, I mean, what do you have here? 3, 7, 8. You've got 8 total books. But if you treat the math books as one group, then you have 3 plus 1 plus 1. You have 5 things. Five things. In other words, 3 novels, 1 math group, and 1 biology book. So in how many ways can these be arranged on a shelf? Well, this is obviously 5 factorial. Right, which one comes first? You have 5 choices for the first one, 4 choices for the second, and so on. So 5 factorial choices, but now your math group consists of 4 books. So imagine changing those around inside the group. How many ways can you arrange these? Well, which book comes first? You have 4 choices for the first book, and then 3 choices for the second, and so on and so on. So 4 factorial choices inside the group. 5 factorial times 4 factorial. There should be a tutorial this week. When is it? I'm not exactly sure what day. So let's start with that. What day of the week is it normally on? Because as you know, today is Tuesday, but other days might follow a Monday schedule, I believe. Wednesday or Thursday. I believe, I think Thursday follows a Monday schedule. What about Wednesday? Well, I'm not sure. I strongly suspect that you have tutorials this week. All right, so there it is. There was another question about something or other. 8 men and 6 women. Yes. Look, yeah. So the midterm / final exam situation. There has been no decision made by the department. Consequently, it has to, it's too late to change anything now. So midterm grades will stand. There have been issues with some people. So there has been some cheating. These will be reported. The final exam will be a 72-hour take-home final exam. And the same thing goes for the final exam, meaning cheaters will be reported and websites will be monitored, discussion forums, and that kind of thing. And, look, this should have been a relatively easy class. There's really absolutely no need for these types of things. But if you feel you need to cheat in order to pass, it's very unfortunate. And, you're putting your future at McGill on the line by doing that. How would I scale the finals level of difficulty 1 to 10? Well, how would I scale this class on a difficulty of 1 to 10? 10 being the hardest, 1 being the easiest. I would say that this course is a 1. You can't get any easier than this course, I don't think. On a scale of 1 to 10, where 10 is the hardest, again, as far as the midterm is concerned, I would have described the midterm as a 0. It's so easy. Now, how do I scale the final exam difficulty on a scale of 1 to 10? Well, if I compare it to the midterm, I'm going to say that it's an 8. I wrote the midterm last night. What can I say? It's long. It's long. It's long and computationally heavy. Let's say that. Yeah. Is this not going to impact students that don't cheat? Well, what I hope is, here's my hope. First of all, if you're just copying from somebody else, I mean, I think it's going to be obvious. Right now, I have 10 questions. It can be completed in designated 3 hours. I mean, it took me about an hour and a half to do. Yeah. I mean, sure, cheaters will find a way, but I think it's going to be obvious to the marker. And like I said, they will be reported. Yeah, I hear you. Well, I mean, maybe I'm unrealistic. I don't know. I thought the midterm was so easy. I don't know. Maybe it's all. I mean, look, it's all on material we have seen. Yeah, it is a frustrating situation. Absolutely frustrating for everyone. I mean, look. Let's. Here's the thing: if you're comfortable with the material, there's no reason for you not to do one. Is it weighed more on the content after the midterm? It's probably. I think it's evenly distributed. What do I expect the average of the class to be after this exam? Well, who knows? Who knows? I mean, look, what I attempted to do was to make do I want to say a cheat-proof exam? I don't know that I want to go that far. But yeah. It has to be your work, or else it'll be clear that it's not. That's the thing. So that's the exam I wrote. Yeah. I wrote an exam where it's going to be clear if it's not your work. Well, I mean, of course, you have to show all your work. So, yeah. Plus, you know very well that there are sometimes more than one way to do things, and there are checks and balances to make sure that you have the right answer and this and that. So there are ways. I mean, I would like that everybody would get 100 because they can check their work and. All right, thanks. Enough of that. There was a question about men and women that didn't want to work together. I don't know. You want to make a committee of 3 men and 3 women. when two women don't want to work together. Would I recommend writing sentences explaining choices and answers? I mean, in these kinds of counting arguments, I mean, you're certainly welcome to do that. You're certainly welcome to do that. If you're row reducing, there's really no point. If you're row reducing, it's clear what you're doing, so there's no need to explain anything. All right. So the question is, how many committees can you make consisting of 3 men and 3 women where 2 of the women don't want to work together? Well, let's count. So here's an example where you might try to explain what you're doing. Let's count the number of committees where those women have been put aside. Right? So you start out with 10 women, but let's remove those 2 women. So you're left with 8 women, and you want to choose 3 of them. So 8 choose 3, and 7 choose 3 for the men. This is the number of committees where neither women are there. And now let's count the number of committees where one of the women is there. You don't want both. You don't want both. But one is fine as well. So let's take one of those women. We'll choose one of the 2. We still need 2 other women. 2 other women from the 8 remaining. And 3 men from the 7. There it is. Again, here, perhaps a nice sentence explaining what you're doing would be nice, especially if a mistake has been made. Right? I mean, if there's no mistake and it's perfect, then we're good to go. But if a mistake has been made, a sentence might give you some hard marks. How are we doing here? Questions? Last time we introduced the idea of expected value. Right, let me introduce the expected value of a random variable. Is sometimes referred to as the mean. And is denoted by the Greek letter mu. Mu, the mean, is the expected value of the random variable. And now, given a random variable and its mean, we would like to measure how much the random variable varies from the mean. So given a random variable x and its mean mu, we wish to measure how much the random variable varies from the mean. And we're going to do that by considering the difference between the random variable and the mean. But as you know, x can take on different values. So we want to go through those values. And this could be positive or negative depending on what values x takes on, right? Some may be less than the average, others may be more. So we don't want negative and positive values. We'll make everything positive by taking the square. And you want to cycle through all of the values. So we're going to take the expected value of this expression. This will allow us to pick up all the values of x, all the values the random variable takes on. And what is that? Well, I mean, if you square this is x squared. This times 2. And that squared. And what is this? Well, I mean, this is this expression times all the, right? I mean, if you have a probability distribution, so the values a random variable takes on along with the probabilities, right? This takes on x1 with probability p1, x2 with probability p2, and so on all the way to xn with probability pn. And if you have a probability distribution for your random variable, what is this? Well, this is the value squared. So this is x1 squared minus 2 mu x1 plus mu squared all the way times the first probability, and so on for everything else, right? x2 squared all the way to the last one. as you know, right, imagine expanding that and grouping everything together, right? So, I mean, let's expand. So this is x1 squared times p1. And, you know, let's just group these, x2 squared times p2 and so on, all the way to xn squared times pn. And then minus 2 mu x1 p1 all the way to minus 2 mu xn pn, right? So I'm going to group the middle terms together. And finally, the last terms. Mu squared p1 plus mu squared p2 all the way to mu squared pn. Here, this first term is the expected value of x squared, right? I mean, it's x1 squared times p1, x2 squared times p2, and so on. So that's just the expected value of x squared. Here, if you factor out a 2 mu, a minus 2 mu, what do we get? x1 p1, x2 p2, all the way to xn pn. And here, if you factor out a mu squared, what do we have? p1 plus p2 all the way to pn. Let's take a step back. What is this in the brackets here? x1 p1 plus x2 p2 all the way to xn pn. Well, that's the expected value. So that is 2 mu expected value of x. And here in this bracket, p1 plus p2 all the way to pn, well, this is a probability distribution. So you know the probabilities better add up to 1. So this bracket should add up to 1. Now the expected value is precisely mu. So this is the expected value of x squared minus 2 mu. This expected value of x is mu. So this is really expected value of x squared. This is 2 mu squared plus mu, so that's minus mu squared. Or the expected value of x squared minus the expected value squared of x. This expression is equal to that. And this is a measure of how much x varies from the mean. This is known as the variance. Since this is the expected value of a positive term, right, because it's squared, times the probabilities, which are themselves always positive, this variance is something that is always positive. So we oftentimes denote it by sigma squared. where sigma, which is the square root of the variance, is known as the standard deviation. Let me bring your attention to the fact that this is not in the book. This variance and standard deviation are not in the book. The book has something they call variance. Please disregard that. It is not this variance. So don't be confused with what the book does. What the book does is not variance, but something else. Questions here? Let's take a few examples. Consider the following scenario. A delegation of 3 is selected from a city council made up of 5 liberals and 6 conservatives. So you've got 5 liberals and 6 conservatives. You want a 3-member delegation. How would we practice if it's not in the book, right? It's a valid question. There will not be any variance questions on the final. But that doesn't mean we can't do some together. And let's do one. And how would you practice? Well, I mean, exactly the way we're going to do it. I mean, of course, you won't know if it's the right answer, but you'll see that there's not much happening here. We have a 5. We want a 3-member delegation made up of 5, well, coming from 5 liberals and 6 conservatives. What is the question? What is the expected number of liberals in the delegation? Right, the question isn't asking us for variance, but we'll work it out nonetheless. Right here, they're just asking for the expected value. So let's introduce a random variable. Let X be the number of liberals in the committee or in the delegation. What values can X take on? How many liberals can you have in a 3-member delegation? Thank you, Bryn, right? I mean, you're either going to have 0 liberals, or 1, or 2, or 3. Absolutely. Now, what are the probabilities associated to that? Well, I mean, we have 11 people in total, right? So in how many ways can a 3-member delegation be chosen from 11 people? That is 11 choose 3, right? So we'll do a probability associated to that, but your whole sample space, how many groups of 3 people can be made? 11 choose 3. Now, what do we want? If there are no liberals in the delegation, that means that the entire delegation is made up of conservatives. So 6 choose 3. You're going to choose the 3 people from the 6 conservative and 0 from the liberals, right? I mean, if you want, you could throw in a 5 choose 0, meaning no liberals and 3 conservatives. Or if there's 1 liberal, right, you want to choose 1 from the 5, and the other 2 should be chosen from the conservatives. So 6 choose 2 over still 11 choose 3. And for 2, you're going to choose 2 liberals from the 5 and 1 more delegate from the conservatives. And finally, 5 choose 3, 6 choose 0 over 11 choose 3. Convinced? Let's clean that up. Let's work those things out and make sure that we actually do have a probability distribution, right? Let's make sure that the probabilities actually do add up to 1. What is that? So let's rewrite that here. So 6 choose 3. This is 6 factorial over 3 factorial 3 factorial. And this is 11 factorial over 3 factorial 8 factorial. We can cancel some of these. This is 9 times 10 times 11. And this is 4 times 5 times 6. 4 times 5 times 6 over 9 times 10 times 11. If the order did matter here, we would use permutations instead. Absolutely, right? If this delegation had some sort of status where you had a president, VP, and secretary kind of thing, then absolutely the order would matter and we would use permutations. Here, this is 5 factorial over 1 factorial 4 factorial times 6 factorial over 2 factorial 4 over 9 times, yeah. So what is that? That is 5. This is 5. This is 5 times 6 over 2. And this, you have a 3 factorial on top. So another 6 over 9 times 10 times 11. This simplifies a bit. 5 and 10 cancels, that's 2. So that's 2 times 6 is 12. 12 over 99. And what about this? This and that cancels to give us a 2. These two 2's cancel to give us 3 and 3. So this is 30 over 99. For the 2 business, 5 factorial over 2 factorial, 3 factorial, 6 factorial over 1 factorial, 5 factorial over 11 factorial, 3 factorial, 8 factorial. Let's cancel this and that. So this is 3 times 4 times 5 times 6. Over 9 times 10 times 11. This and this cancels to leave me with a 2. Let's take a 2 out of here. That leaves a 3. 3 times 3 is no, we'll leave the 99. So 9 times 4 is 36 over 99. And thank you, Anne. And has worked out the last one to be 2 over 33 or 6 over 99. Let's make sure. Let's make sure that these add up to 1, 66, 76, 77, 78. I think we're slightly short here. Let's see that last one. I could have made a mistake somewhere else. 5 factorial over 3 factorial, 2 factorial, 6, this is just 1. These cancel out. That is 3 times 4 times 5 over 9 times 10 times 11. This and that cancel, leaving me with a 2. Oh, that is right. 6 over 99. Something has gone wrong. Where did I mistake is in the second one? Thank you. What should it be? 5 over 11, so 45. 45 over 99, let's see. 70, 81, 91, 92, 93, 99, very nice. Very nice. Let's see what has gone wrong there. We had 5 factorial over 1 factorial, 4 factorial. 6 factorial over 2 factorial, 4 factorial. I'm just redoing the second one. Over 11 factorial, 3 factorial, 8 factorial. So this and that cancels if you do 9 times 10 times 11. We'll flip it. This is just 5. This and that cancels, leaving me with 5 times 6. over 2. So that's 5 times 3, and then I have a 3 times 2. Over 9 times 10 times 11. 5 and 2 cancels with this 10. 6 times 5, still 30. What am I doing? What am I doing wrong? Where 3 times 3 is 9. 9. 9. Thank you. Thank you. 3 times 3 is 9. 9 times 5 is 45. Nice catch. Thank you, Joseph. All right. So let's save some room here. See, I keep warning people not to make the same mistake. And yet I keep making the same mistake. All right. So there it is. We have this probability distribution, right? I mean, everything adds up to 1. Very nice. Let's work out the expected value. The expected value, right? How many, because that's what the question was asking, how many liberals would you expect in the delegation? So that is the sum of these products, right? 0 times 12 over 99 plus 1 times 45 over 99 plus 2 times 36 over 99 and finally 3 times 6 over 99. What is that? That is 72. 72 plus 18, that is 90. 90 plus 45 is 135 over 99. Is that correct? Does everybody have that? Thank you, Lenny. Right, so we have worked out the expected value of the number of delegates, number of liberals in the 3-member delegation. I mean, let's make sense of this number here. I mean, 15 over 11, fine. Thank you. Thank you. So let's make sense of this number, right? Because you understand that if you take a delegation at random, you're never going to have 15 over 11 delegates, right? Because the delegates are whole numbers, right? You either have 0 or 1 or 2 or 3. You're never going to have 15 over 11. So what does this mean? Well, this means that if you, I mean, it's an average, right? If you took enough delegations at random and counted the number of liberals there were, then you would get something close to 15 over 11. Or equivalently, if you chose 11 delegations at random, you would expect 15 liberals in total. So that's why we say the expected value is a weighted average. You never expect to find 15 over 11, so 1 point something delegates, 1 point something liberals in a delegation. Of course, it's a whole number, but that's what this means. Exactly, right? As Asma suggests, we could see it on a larger scale. If you had 11 delegations, you would expect 15 liberals in total. That's the idea. Now, let's calculate the variance. So here, mu, this is your mu. Mu is 15 over 11. Let us calculate the variance, which is the expected value of x squared minus the expected value squared of x. Right, we already have this. This is mu squared. So all I need is the expected value of x squared. So let's work out the expected value of x squared. All right. I mean, what values does x take on? Well, it could be 0. So 0 squared with probability 12 over 99. Plus 1 squared with probability 45 over 99. Plus 2 squared with probability 36 over 99. And finally, 3 squared with probability 6 over 99. What is that? This is 4 times 36. So 12, so 120 and 36. 156. 156 plus 54. That's 210. 255. Is that correct? Does anybody have that? 255 over 99? Can anybody confirm? Anybody is still doing this? I can only assume 255 is wrong. Anybody have something different? No, it's probably me. 9 times 6 is 54. 54 plus 45, that's 99. And this is 4 times 36. Oh yeah, I see the mistake already. This is 12, 144, there it is. So 243, 243, thank you. $243 or 27 over 11. Thank you. And And consequently, the variance is the expected value of x squared, so 27 over 11, minus the expected value of x all squared. There it is. What is that? 27,297 minus 225 over 121. 72. 72 over 121. Anybody? Is that correct? Thank you. There it is. So that's the variance, and the standard deviation, or sigma, is the square root of that. 72, root 72 over 11. How can we interpret the answer? An excellent question. What does this really mean? Well, we haven't gone into the whole theory behind variance, but like I said, variance measures how much the random variable varies from the mean, right? So, I mean, here are the possible values your random variable takes on, right? So your random variable could be one of these four values, and here your average, your mean, is 15 over 11, so I mean something around here, 1 point something. So you see, the question is, how likely is the function able to take on the values very far from this? That's what the variance measures. How likely is it that you're going to take 3 on? And we have our probability distribution in front of us. Unlikely is the answer. And this is reflected in the variance itself, right? This number is fairly small, right? I mean, it's less than 1. In other words, most of the values your random variable takes on are situated near the average, near the mean. And so this is reflected by a small variance. If the variance is very large, right, because think about what's happening. I mean, we're using this as the definition, but it's also the expected value of x minus mu squared. So if this takes on a large value, right, the expected value could be very large. This expected value could be very large. And this would tell us that the probability, I mean, even if the average is small, the random variable could take on values which are much larger. So that's the interpretation of a small variance versus a larger one. There's a lot of theory associated to this that we did not discuss, but associated to the standard deviation. If you look at your mean plus or minus the standard deviation, that gives you an interval where most of the values the random variable takes on has to live. There's some nice theory behind that, and this idea of mean and variance extends to, here we're doing discrete random variables, right? It can only take on a finite set of values. What if your random variable could take on a continuous set of values? And you get these nice things ranging from normal distributions, the bell curve, and all of that. All of these things occur nicely, and you might encounter them in a course. Well, normally you would see them in a course on probability, but perhaps in your case, you might see them in a course on statistics. Statistics and probability are very intertwined. All right. But there it is. This is perhaps a good place to end today's lecture, and in fact, the whole course. Unless you've got questions, I think Brendan has a question here. How would you proceed on choosing, for example, president, VP, and secretary while accounting for the number of liberals? Good question. Good question. Also the final question, yes. Final question. So let's talk about that final question. The final question, if you read it properly, it's asking you for the expected value. Right, so the expected value, and of course you understand that what you're dealing with is a binomial distribution. The problem is that you probably don't want to use a tree or you don't want to draw a tree or draw a probability distribution because you have 19 trials or some other crazy number that you don't want to deal with. Interestingly enough, you can prove that if X follows a binomial distribution, let's write that down. If X follows a binomial distribution, and N is the number of trials, if N follows a binomial distribution where P is the probability of success, and N is the number of trials, then the expected value of X is NP. You can prove that. We don't have the tools to prove that, but yeah, but this can be proven. So in that last question, you'll convince yourselves that we have a random variable that follows a binomial distribution, expected value, NP. Back to Bryn's question. How would we go about the number of liberals if the order did matter? And Asma is suggesting permutations. Absolutely. Absolutely. I think the case for zero is easy. Right, the case for zero is easy. What do we want? We want the, so what did we have? We had 5 liberals and 6 conservatives. So 0 liberals, how does that happen? The people are chosen from the 6 conservatives. So this is P 6, the number of permutations of 6 elements taking 3 at a time, right? Here the order does matter. 6 times 5 times 4, absolutely. This is over the number of total ways you can choose 3 people committees where you've got, right, so 11 choose 3. Right, well, not 11 choose 3, but the number of permutations of 11 objects taken 3 at a time. And if you don't, I mean, if they're all liberals, then you want the liberals to be chosen from the 5. So this is P, number of permutations of 5 elements taken 3 at a time. Still over the same denominator. I mean, it's always going to be the same denominator, right? The real question is, what happens if you want 1 liberal? One liberal. So, I mean, we have 3 positions where the order does matter, right? So either president, VP, or let's say secretary. So let's say that you have a liberal as the president. Right, exactly. But let's argue. Let's argue what the answer is going to be. Suppose, right? So here we just want 1 liberal. So suppose the liberal occupies the presidency. how many other ways can we have the VP and secretary being conservatives? This is going to be P62, right? You want to choose 2 people from the 6 conservatives. So if your liberal is set, that's it. Now you have 5 options for the liberal president. So it's going to be 5 times that. And that's just when it's the president that's a liberal and the other 2 are conservatives. But if you move this around, if the liberal is the VP instead, then of course it's the same thing. And if the liberal is the secretary instead, of course it's the same thing. So you have 3 of those. So this is 3 times 5 times P62. Again, the so P62 is the 5 times 6, and then you have 3 times 5, exactly as Bryn suggests. And the same idea, but in the reverse for the 2, right? Instead of thinking 2 liberals, you could think of 1 conservative and do a similar argument. But it's not. Instead of thinking 2 liberals, think of 1 conservative. 2 libs or 1 conservative. So if you do the 1 conservative case, here those 2, you want to choose from the 5 liberals. So that's going to be P52. And then you have 6 conservatives, so 6 of these things. And then move the conservative to the VP, and then move it to the secretary, so 3 times that as well. So 3 times 6 times P52. You can probably do it a different way as well. Absolutely. Now, a nice exercise is to clean that up and make sure that you have a probability distribution, right? Make sure that the sum of the entries adds up to 1 so that we haven't made a mistake. This is final exam material, absolutely. Tricky, but we've done quite a few. All right. Thank you all for coming. I'll have office hours on Thursday as well if you need to see me. And if there's anything, you can always email me as well. Good luck on your final exams, everyone. If I put a question like this on the final, I would not steer you in any direction. You could answer it however you wanted to. You got something different for 1 liberal? I've lost you now, but is it really different? Is it really different? So here's my suggestion to you. Work this out and then work it out your way and see me during office hours on Thursday. We can discuss it, if it's different or not. All right. You guys have a good one. I will see you on Thursday during office hours if you need me. Otherwise, good luck on your finals. Have a good one.